Now I'll start by working, I think, the C choice on this one. And if you look here on the C choice, the 2 minus 2x is what we've been calling M. The 3y squared is what we've been calling N. And we know that the M is the partial derivative of this magical potential function with respect to x, and that the N is the derivative of the potential function with respect to y. Now, if the partial of phi with respect to x is 2 minus 2x, we can recover some of phi by doing the integral of that. So if we integrate with respect to x, we can at least get some of our phi. So we know that phi is equal to, this would be a 2x minus 2x squared over 2, which would just be x squared. Now, when you're doing multiple variables, in this case we're assuming that there could also be a y, since this is a partial derivative, that means that the constant of integration that we come up with could be some function of y. We'll just use the h for the some function of y. So then, if that is the case, let's see what the partial derivative of this with respect to y would be. The derivative of 2x would be 0, as there's no y in it. The derivative of x squared would be 0, since there's no y in it. So we'd come up with just the derivative of the y, which we'll just say is h prime y. Well now, if the partial of y is h prime y, and the partial of y is also n, then we know that the h prime y is equal to 3y squared. And we can integrate that to get h. The integral of 3y squared would be 3y cubed over 3, which would just be y cubed. So then, our potential function would be a 2x minus x squared plus ay cubed. And we're ready to write our solution, which is simply that equals some constant. Now, since this is a y cubed, we could somewhat recover our y function. So if we subtract things from both sides, we would have c minus 2x plus x squared equals y cubed. And so y then would be the cube root of that. So now let's consider the g function, or the part g, trying to recover the function. So we have this, which is our partial of phi with respect to x. And then we have this, which is our partial of phi with respect to y. Now again, it doesn't really matter which we start on. Let's just say that if we take the x e to the y, the partial of phi with respect to y, we can integrate that with respect to y, and we'll come up with, here we just, since x is not what we're integrating with respect to, we just copy down the x and do the integral of e to the y, which is still just e to the y. Now, since we're integrating with respect to y, that means our constant of integration could be some function of x. So we end up with this much of phi recovered so far. Now we'll do the derivative of this with respect to x. That comes out to be e to the y, and that is the derivative with respect to x. Now we want that to be equal to that. Now the e to the y's are going to subtract out. We get h prime of x equals 1. We can integrate both sides of that and get h, the integral of 1. We're integrating with respect to x, by the way. The integral of 1 would just be x. We don't need to write the c on that. And so our potential function then is x e to the y plus x. So our solution would be x e to the y plus x equals some constant. We'd like to recover the y if we possibly can. So if we subtract x from both sides and divide by x, we can do the natural log of both sides and get y equals the ln of c minus x over x. Okay, we'll work on the A choice on this one. And to begin with, we're asked to verify that it's not in exact form. So here is our m and n. To check for exact form, we need to do the derivative of m with respect to y. The derivative of m with respect to y would be a 6y squared. We need to do the derivative of n with respect to x. The derivative of n with respect to x on this first term would be a 12x squared y cubed. And the second term would be 3y squared. So obviously they are not equal to each other, therefore it is not in exact form. Now we could possibly have to look at two different combinations to get this into exact form. One is, how about if we do the partial of m with respect to y minus the partial of n with respect to x divided by n. Now if we can make that come out to be a function of x, then we can find an integrating factor. So this is 6y squared and 12x squared y cubed minus 3y squared over 4x cubed y cubed minus 3xy squared. So if we simplify this by removing the parentheses, distributing the minus sign, we end up with a 9y squared and a 12x squared y cubed. And in the top, it looks like we can factor out a 3y squared, which gives a 3 minus 4x squared y. In the bottom, we can factor out an xy squared, Now notice that these two terms look a lot alike except opposite signs, so we can take a negative out. I'll just do that right here. Take a negative out here, which would make it a -3 and a positive. So these then would cancel. The y squareds would cancel. We'd end up with a -3 over x. So that is a function of x. Therefore, we can do our integrating factor, which would be e to the integral of -3 over x. The integral of -3 over x would come out to be a -3 ln of x, which is the same as the ln of x to the -3, and e to the ln of x to the -3 just comes out to be x to the -3. So we should be able to take our original differential equation, multiply through by x to the -3, and turn it into exact form. So this would be 2x -3 y3, and this would be a 4, the x cubed and x -3 will disappear, y cubed, and this x would come out to be -2, and so this is our partial of phi with respect to x, and this is our partial of phi with respect to y. We need to integrate either the right one with respect to y or the left one with respect to x. I kind of like the looks of the left one, so we'll do the integral then of 2x -3 y cubed with respect to x. That comes out to be a, with respect to x, that'd be x -2 over -2. So the 2's will cancel. We'll end up with a -1 x -2 y cubed. And then our integrating factor would be some function of y. Now we'll do the derivative of that. The derivative of that with respect to y comes out to be a -3 x to the -2 y2 plus the derivative of the h. We combine that with that, set them equal to each other, and as you can see, that's going to subtract out. We get h prime y equals 4y cubed, which when we integrate that would give us h equals 4y to the 4 over 4, which is just y4. Therefore, our phi comes out to be a negative x -2 y3 plus y4. And our solution would be phi equals some constant. Now, obviously, since y is to the 3 and to the 4, we're not going to be able to recover the function of y, so we'll just pronounce that the solution.